the concentration of one thing, it shifted to the other. That was pretty straightforward, intuitive for everybody, if I recall. Then we looked at pressure, a little less intuitive. There, what mattered there when we looked at pressure and the direction that that could influence whether or not a reaction in equilibrium would move to the left or to the right? How many moles of gas? First, if you had a gas, let's start, right? Then if you had more moles or less moles on one side versus the other. Because if they were equal, then it doesn't matter. You can't determine anything with pressure. If you had that, and you had pressure, a greater number of moles on one side of the arrow than the other, and you increase the pressure, would that push it away from that side or towards the side with more moles? Away. Because the side with more moles is the side that has an increased amount of pressure. So if you increase the pressure, it's going to shift it the opposite. And if you pull it away, it will shift it towards it. Okay. And I think we did some examples. I can't recall. Did we do this one? I think we did. Pressure increased, volume is decreased. This is the stress. I have 3 moles here and 1 mole, 4 moles and 2 moles. This looks really familiar from Third Tuesday, does it?
We did it.
Yeah, okay, we did it. Good. So we can go forward. This little thing, did we do this one? 1 mole of gas, 2 moles of gas. This also looks familiar. Yeah. Okay, good. Okay, so we did this. Good. Okay, so you guys already know how to do this. Did we look at this here? I don't remember looking at this picture here. This is an illustration of everything I've already said. Okay, essentially. So if you're caught in your studying and you're not sure, look at this particular concept, look here, and you can see here you have a container and you have a piston here, which means that I could adjust the volume accordingly. So let's say it starts here and I push the volume down. What does that do to everything inside of it? It increases the pressure. What's in there are these 3 things here, which are represented by these little colors, which are here. So if I push, so the first thing I look at, here's the equation. I have 1 mole, 3 mole, 4 moles on this side, 2 moles on this side. I decrease the volume, I increase the pressure, then I shift the one with more moles that has a greater pressure the opposite direction. Right. And this is just an illustration of that. You can see the arrow here. And if I were to open up the container a little bit, so I increase the volume, I decrease the pressure, and therefore would then favor the side that had more pressure on it, which means more moles. Okay, and that moves it from left to right, or from right to left here. Is that okay? This is just an illustration of everything we've already done, but if you're studying and you get confused on this concept, you could look back at this picture. It should help out a little bit. Okay, the last thing is the effect of temperature on the change in equilibrium as a stress. So once again, there's always a temperature at the whatever equilibrium you've already established. That's not what we're talking about. We're talking about once you have that established and then you do something and put pressure on that system. In this case, I'm going to add energy to something. Or I'm going to pull energy away. And then what happens to the equilibrium? How does it shift? Okay, that's the third concept here of Le Chatelier's principle that we're going to look into. So the same thing as before. A lot of words, I'll let you read this. What I will do, okay, this is a nice little reminder. If I have a chemical equation, say CH4 plus O2, and it goes to CO2 plus H2O, that should look really familiar. Combustion reaction. What happens here in terms of energy in this type of chemical reaction?
Energy on the other side?
You get a whole bunch of heat as associated with this. So if I do this from here, see it's a single arrow, not an equilibrium, and then I get this, I also gain a lot of energy from this. In other words, it's very exothermic, if you remember that term. Energy came out of it. When I get energy from a reaction, then I could also say, if you recall from 101, that that's a product. Right? Because I gained it as a result of these 2 things happening. So I could put here plus energy, let's just say, whatever that is, usually in kilojoules or whatever else. Okay? Now, if this happened to be in an equilibrium, which this type of reaction isn't, then if I added more energy to this system as a stress, which way do you expect it to move? The opposite way. Le Chatelier's principle. It will try to relieve that stress. And it will shift this way, the same thing as everything else. Okay. Now, if this reaction, let's reverse this and say this is happening here. So just think of that twisted, so I don't have to rewrite it. What happens here? Energy went into the system in order for this to happen, right? I had to put energy in here. Remember now, these are my reactants now. And that in order to get this. So that's endothermic, just to remind you, right? And so this would now be on the reactant side. And so then if I put in energy in this situation here, it's still going to shift to the left if it's in an equilibrium. But if I put in energy over here, what's going to happen?
Exothermic going to the other side.
Is it still in equilibrium
We're going to assume these are in equilibrium when I'm talking about Le Chatelier's
or
principle.
shift it to the other side?
Got to shift it to the other side,
Right.
right? Same thing as with concentration. So wherever I'm adding energy to or away from is the same thing as if I'm putting in a concentration of something on one side or another. I'm just saying the energy, just like I did the pressure, is a reactant or a product, and if I add more to that side, it's going to shift it to the other. If I add less to that side, it's going to shift it towards it.
Right.
Okay. Okay. So that's what the foundation of this is. Let me add one more thing. When we're putting in energy into the chemical equation and it comes out as a product, you put it as a positive on the right side. If you put it in order for the reaction to occur, which means it's endothermic, then I put it as a reactant, as a positive on the reactant side. I could always take that and just subtract out and have a negative on either side. So that actually is right, but it doesn't, it's not the right, it's not a good way to do it. It's very confusing. So if you're putting energy in, you put and you want it in the chemical equation, then you put it on the reactant side. If you're getting energy out, you put it on the product side. When I take it outside of the equation, it's now delta H, enthalpy, if you recall, right? So that's usually, what is delta H enthalpy? How do we usually state that in units?
Kilojoules per mole.
Yeah, some energy per mole, right?
Right.
And so then, if it's, actually, let me make sure I write this because, do I have it here? Let's just go, let's do the same thing. CH3, CH4 plus O2 gives me CO2 plus H2O plus energy, okay? Let's actually give this a number. So I can put a number here and say plus 125 kilojoules. Now, if this automatically tells me it's exothermic, right, because it's on the product side. If I want this in enthalpy, delta H, knowing that this is exothermic, that means I lost energy, and in the concept of delta H, that now becomes negative.
Right.
Okay, so this here, seeing it here, would mean that it's a negative 125 kilojoules, which just means that 125 kilojoules was lost from the system to the surroundings as a result of this reaction here and however much I used. Right, because remember I could also use it in here as a molar ratio, if you recall. Right, if I wanted to find out how much, depending on how much I started, what certain number, mass, grams, whatever. And then delta H, if your number is on the left side, that means that it was endothermic, and then this number becomes positive when you pull it outside of the equation. But inside the equation, they're positive either on the left side or the right side. I had a question here? Did that cover it?
Yeah.
Okay. Okay, so that's just a review from 101. Okay, so that's what they're showing up here. And of course, this is just so that you can see what happens in an equilibrium and Le Chatelier's principle and the adjustment it's going to make as a result of adding or taking away some amount of energy. Okay, so here, and I'm going to assume this is a constant pressure. I have N2 plus 3, so this is the same equation we saw before. This is the synthesis of ammonia. And this time, we're adding heat here because as a result of this, this must be exothermic because I see heat on the right side.
Right.
Okay, which means that it's a negative delta H. So, or
May I say something?
they're not actually stating that. They're saying they're adding the heat. No, this is right. Then on top of that, they're saying here that they're adding heat to this whole system.
Okay.
Okay? As they had, it's awkward, right? As they add heat to this whole system, then what happens? The side that has the heat, it will shift away from it.
Right.
And so it shifts to the left. Okay. They're also stating one more thing, which is something I didn't really talk about in terms of the shifting with pressure or really concentration. I might have talked about concentration, I can't recall that far back, but Tuesday, right? But having said that, it does mention something about K here. So in this relationship, before I add this, just this here, what is my K? It's gonna be this squared over this cubed over that times that, right? If I'm shifting this reaction this way, I'm making less of this and more of this, and we did cover that, remember? In the, and there's one slide, I think a couple of you had questions of after class.
Oh, yeah.
Right, where if I increase one, you get the A, B, C, D, and then it becomes A prime, B star, C prime, D prime, because some side lost some side gained one, and the one that actually you increase has more than it started with, but less than it had after you added, right? So that's kind of what it's saying here. So I'm gonna have less of this, more of these, and as a result, what happens to K?
Yeah, smaller K.
It gets smaller, so they're putting it in context in that way as well.
It's the product of.
Right, just so that you can see what's actually happening in the equilibrium as a result of the change in the shift based on the stress. So in this case,
Of the original equation,
yeah,
reaction.
from the original. So in this case though, so I could ask a couple questions here. What if I increased H2 here,
H2.
concentration?
Oh, then it goes back to the
Shifts
right.
to the right. What happens if I decrease the pressure?
Then it goes to the left.
Goes to the left. See, in this one equation, you can see all three things happening based on how I ask.
Right.
And as a result, what happens to K? If I shift it to from left to right,
It's
K
a-
goes up. If I shift it from right to left, K goes down.
Right.
And those are the major concepts.
When you shift it from right to left, that would be called a reverse shift because you're going back. And then the other.
I
way
don't know if I would
forward.
call it that because you could potentially just take this whole thing and flip it. And that's what we did when we played with K's, right? And that was called reverse. And that's a different thing than what you're suggesting.
Okay.
You're saying you're leaving this here and you're just calling it reverse. And I don't want you to become confused with the term reverse when you're playing around with the K's,
Okay.
right? I saw another hand come over here. It wouldn't, I mean, from a English perspective, that would be okay, yes, right? But it could confuse you in what it actually means and maybe what the traditional
Decay.
terminology is.
Decay was the product over the reactants. So if
Yes.
you flip it around,
You switch, yeah, then
If-
it's
if you-
reversing it,
but then the
You get the negative.
the product will become reactants.
becomes negative. Remember, we did that with K's.
Or negative, right?
Right, it just becomes negative. Same thing as if we, take half, 1 1/2, 1,
Right.
then how does that shift to K? Remember, we did all that?
Right.
In fact, I think that was Nathan that presented that, right?
Right.
Or started it, something like that. Okay,
Okay.
so we get a sense of what's happening here. So, and by the way, these things are relatively easy. Just keep them straight in your head because on an exam, you get a bunch of different things. Things start to become confusing. All of a sudden, ideas that you think you know, you don't know. So this is a nice little thing to put on your card or your page, where you just lay it out really quickly. So in case you get confused, you can look at that. Right, that would be a good one to help you solve a couple, multiple choice style questions or whatever.
Right.
Okay, what do I have here? Okay, so here I do this same thing. It's really simple. I wish they'd give me something different here. They just remove the heat here. So then obviously it goes towards it as this shift in equilibrium, and therefore K gets larger. No big deal there. If you understood the first one, this one should be pretty straightforward. Okay. I have a different good. N2O2 plus heat gives me 2NO2, and it's kind of nice so that if you're doing these kinds of reactions, you really like this kind of thing where this is colorless. Without it, does seems like you're not adding anything here. It becomes brown, so you could actually see the reaction, so you could visualize what's happening.
Okay.
That's always really nice. It's got a built-in indicator essentially, so that's really really nice. A lot of things don't have that. In fact, when they don't have it, what would you use? Like phenolphthalein, right? Out of curiosity, it's funny. I think my 101 class used that either this week or last week. And when you guys used it, I don't think I mentioned this, but maybe I did. What's going on with phenolphthalein? Like, if I were to put something in as an indicator into one of these reactions, what is it? What's really happening?
Oh yeah, you did explain it with the graph. You actually graphed it. That you put a line in
Okay.
it, and like how it actually shots up. at
It's
a
its own
certain-
chemical reaction.
Right.
Right.
At a pH.
It's just a different chemical reaction going on based on what you're producing in your product. versus what you had in your reactants, and it's now we're going to learn that, I think, maybe in the next chapter. The next chapter is acid bases, which we're going to start today. I think it's acid and bases, right? We'll take a look. But so I think later on in that, we're gonna actually learn how you determine an indicator. So like, how did we come up with phenolphthalein as? And is that even a good indicator? The presumption is yes, because we gave it to you. It's easy to use. It actually doesn't cost a lot, everything else, but it isn't the ideal indicator, by the way. And you'll see that based on the chemical reactions and where it's actually causing that pH, where the pH changes for it to change colors. It's a separate reaction. So I wanted to bring that up only because we're going to move towards that. And I just noticed that they had these two things here, so I thought, might as well make use out of that. I don't think they have an actual reason for having it in here for this. So here I'm just this is the system. I'm adding heat to this system. So I'm increasing this side, which means it would automatically, based on Le Chatelier's principle, readjust the equilibrium towards the right and increase this and decrease this. And that's what it says, shift to the right. So if I increase this and decrease that, I also get an increase in K. Okay. Then if I, looking at the same, this is kind of a repeat using a different equation here. In this case, I pull it out. If I pull it out, that means equilibrium adjusts itself to shift to the left, and therefore the K gets smaller. Okay. No big deal, just redundant a little bit, but hopefully that helps drive home the point of what's happening. Any questions on the effects of changing something, whether it be concentration, pressure, which also relates to volume, make sure you're understanding that connection, and temperature in the context of Le Chatelier's principle for a already established equilibrium and how that adjustment occurs as a result of that change. Okay, so you guys are now ready for the first exam on Tuesday. It will stop here.
Quick question.
I have another, this is the same kind of thing. I'll let you guys look this over, but this says everything I just said. You can just see it in its own summaries.
On that that last equation you put there, removing the heat.
Here?
Yeah.
I remove the heat, so basically it'd be like removing a reactant.
What would you call that? So that was initially endothermic as you're adding the heat to then create
This
the reaction.
equilibrium, if you set this reaction up, it needs, you have to add a certain amount of heat to get this. That makes this endothermic, and the delta H is plus, yes.
Then removing the heat.
So I remove some heat. So now I'm going to shift this towards this direction because I'm removing it. Just like if I was removing some reactant.
Right.
It just shifts it this way.
That wouldn't cause anything as per change into what, exothermic or endothermic, or no?
No, it's the reaction itself
Okay.
is still, so, okay. So the question that you're really asking, if I understand it right, let's say this has heat, right? I'll just use delta for heat, even though it means change when it's outside of it. If it's all going here, then when it's done, there's no more of this.
There's no more, right? Endothermic.
Right. And I think that's how you're seeing it. But within the equilibrium, maybe that's why Dieter brought that point up earlier. I thought it was, intuitive,
Okay.
but because I was trying to show what just an endothermic, exothermic was, but maybe your point was maybe more important there in terms of understanding. This is in an equilibrium, so I'm talking about shifting that equilibrium.
Okay.
But if it wasn't in an equilibrium, then adding heat to this isn't going to necessarily cause it to go back. I think that's what you're asking.
Right.
Is that right?
So
So the equilibrium itself is what's established already.
Exactly.
Now adding or taking away the heat does matter
Change the
in terms of shifting where that equilibrium exists at that temperature.
Okay.
our heat moles have a similar influence?
So you're talking about the magnitude of the influence then. So you want to say, like, is it twofold versus onefold or fivefold if you do the same? No, they're different.
Oh, I guess.
Because you're dealing with concentration as an amount, and you're dealing with heat as an energy. So it's not in a molar ratio per se. Does that make sense?
Yeah.
There is a ratio of the amount of energy, if you know the amount of energy you need, based on a certain number of moles. But that's not given in the, so if I had here, let's say I have A plus B gives me C plus D plus energy. And I know this energy here is, say, 125 kilojoules. then I know that if, and let's say this is 2 and this is 2, if this ratio here, if I had 1 mole of A and I had plenty of B, then I'd end up with 125 kilojoules, right? I would know that. So then I could create some kind of what I think you're asking for on that relationship,
Adding C to the reaction would have happened.
right? Which is not a mole-to-mole rate relationship. It's a whatever amount for A or whatever amount for B or whatever amount I create of C or whatever amount I create of D gives me that.
Okay.
But it's not a 1 to 2 to 2 to 1 relationship within the moles of, in this case, we're dealing with concentrations of the concentrations. So this is a molar relationship. So it's, from that I could figure out the concentration, but the concentrations aren't in this relationship either, just the moles. And so that's why we use molarity, which is moles per liter. Once I get the volume component out, then this applies, and this applies to each one of those. That amount, only that amount.
Okay.
Does that make sense? Is that what you're asking? In some, okay, because it's not a direct, like 1 mole, you can't say 1 mole of energy is gonna give me, 2 moles of C.
Reaction.
Okay.
So I can't, those are different things. I can't say that 5 ATM of pressure is going to give me 2 C.
Right.
You see what I'm saying? Yeah, they're different, entities. So are we okay here, Hurdley? On
Yes.
this screen? Anybody else have any questions
That way.
on this? Okay, oh, go ahead, sorry.
Can we do the first example to make sure?
This one?
Using it, yeah.
First example, I have this, and so,
The first one?
okay, so where is delta H here in the equation? Is it on the right side or left side? That's the first thing you need to identify.
Lowering pressure.
It's on the right side because it's negative, so it's got to be on. That means it's exothermic. It's on the right side. So then, what I'm asking here is, the stress I'm adding to the system is I add heat. So if heat's on the right side, I add heat. It's going to shift it to the left. Right? And then you could say this would go down, that would go up, that would go up. If I take away heat, it's going to shift it towards it to the right, and now this would go up, that would go down, that would go down, and that's why you see it.
So when it's negative, it's
Lowering the volume
exothermic
increases
because you're heating.
Yes, that when delta H is negative, it's exothermic because you're losing it. When you take that negative and you want to put it into the equation so that you can see where it is, it's a positive on the product side, right? So this goes to this side here. If this was a positive, then it would be a positive on the left side or the reactant side because it's endothermic. And then from there, it's easy to see everything happening there. Okay, so that summarizes it. Everybody okay? Everybody understands the exam in here, 11 o'clock, Tuesday.
Quick. There's
It's on chapters 14 and 15. You need a Scantron 882, pencil, 8.5 by 11 sheet, front and back you can use, but only one. Can't make a bunch of them and then exchange them as you need them. Which you shouldn't need one if you have an 8.5 by 11 anyways, right? That's plenty. I think that's it that you need to know for the exam. Hurdley, you have a question?
It was just looking at one of the examples. It says decreasing the volume, that's increasing the pressure, right?
Increasing the volume
Of the reaction mixture is increasing the pressure.
is decreasing the pressure.
Decreasing the pressure.
Yes. Okay, so go
No,
back to
decreasing volume. Decreasing volume.
decrease in volume increases pressure. Go back to here.
Right, increases pressure.
Uh-huh.
Okay, yeah.
Go back to here, and this. Whoops. Am I ever going to get there? Where'd it go?
Why adding a catalyst, no reaction, no change?
This. So you want, if you're looking for the pressure-volume relationship, just look at this one. Oops.
Oh.
Just look at that slide.
Yeah.
Right. That
Yeah.
slide will lay it out for you nicely, which is why I introduced it.
And then catalysts don't do anything on gases?
Catalysts speed up reactions.
Reaction.
They're not used in the reaction, right?
It says the answer it gave us was
I
no
don't know
reaction.
what question you're even referencing. It's not a question I have here, right?
No. It's the last example. Adding a catalyst to a reaction mixture.
Adding a catalyst does what?
It says
What's the question?
No effect.
You're just telling me the answer.
To this reaction. So adding a catalyst to the reaction mixture.
Hold on. So if this is 2 and 1, okay. If this reaction mixture is at equilibrium, predict how Each change below will affect the production of hydrogen. So each one has its own change, okay?
Mm-hmm.
So then you're looking at E, and you want to add a catalyst to this reaction, to the reaction mixture. That should not have an effect. It will speed up but it's already at equilibrium, right?
Right.
So then it shouldn't change it per se, but it could shift it to the right. I'd have to think about that a little bit more, but I don't want to take a class time to do that, so
Okay.
ask after.
Yeah.
It's either it stays the same, or it could shift it.
That's what I was thinking.
It could potentially shift it, but if it's already at equilibrium at that temperature, then there's no more
There's
for it
no
to go.
more production of. Yeah, I got you.
So that's what I would think.
Yeah.
Um,
No, that
Okay,
makes sense.
so now we're going to get into acid bases. This is not on the exam on Tuesday. I want to make that really, really clear. However, it is on the next exam. So it's just as relevant. And it's nice because when I looked through this briefly this morning, I think this morning, or last night, or whatever I did, last year. If I recall, it's pretty basic to start. There's nothing really challenging to start. So that should be a lighter lecture so that you don't have too much to go back over for the next exam, since you're not going to use this on this upcoming exam. So, but this chapter does get interesting and it gets challenging. That much I can tell you. As far as I get today, my guess is nothing is going to be overwhelming for you. There would be a couple things that you need to put in perspective. But when we understand these basic perspectives, it's going to get more challenging. Okay, just to give you that heads up. And it will lead us into ice charts, by the way. Equilibrium, we just finished, right? When in 101 did you ever come across an equilibrium? Acid-base reactions, neutralizations, right? And those were usually in weak acid or weak base interacting with something. I think I should have defined at some level what a weak and a strong acid was. I'll define that more clearly now. But that's when you came across equilibriums, right? You never saw those in any other situation. Even though, having said that, they could be in other situations. The other situations they favor the product a lot more, which is why you usually just see an arrow. But you're going to learn now in how to determine just how favorable they are or aren't. And you're going to use those ice tables, right? That's why we went through equilibrium in the last chapter. That's why this progression works this way. The other thing I'll point out is in the equilibriums, there were only two types of physical states that mattered. What were they?
Gas and solid.
Gases and solids. And oddly enough, when you really think about it, does it really make sense to talk about gases as concentrations? And we do that a lot in that last chapter. Not that common. You think of concentrations, moles over liters, amount. Moles of gas make sense, but volume of gas sort of kind of does. Remember, the gas takes on, if you remember what gases do in the KMT theory, they take on whatever the volume of the container is. So no matter how big I make it, it changes, but then the pressure changes, of course, so we can assess it that way. But for the most part, I mean, you don't really think of those in terms of concentration, but aqueous does make a lot of sense in terms of concentration, right? Those are things in an amount of moles per volume. So acids and bases that create these equilibriums are usually, they're double replacement reactions, which also mean, and neutralization, as I heard over there, right? Which mean what? They're all aqueous. So this is where you would think that the concept of equilibrium, knowing that weak acids, weak bases form these equilibriums, and knowing that they're in a physical state that makes sense to use concentrations, how do you think we're going to solve for something like this? I think I used to say this all the time in 101 whenever we came across this. I don't know if we came across it that often. I think we changed the curriculum a few years back. We used to cover acids and bases. I don't know if I did that specifically in 101, but if I had, let's say, acid plus base, and that became, H2O plus whatever, that's salt, right? It's the traditional one. And if one of these were weak or strong, it went back and forth, and these are always aqueous and whatever. And I would automatically say something like, well, if you have this situation, you had a weak acid, weak base, you have something like 95% of this or more and 5% of that. Remember that?
Mm-hmm.
It's been used to say that a lot, right?
Right.
Where did I come up with this 95 and 5? That's kind of arbitrary, right, according to you guys. I didn't give you any rationale for it. Then so I said, though, it could be flexible, and depending on what it is, it could be 96 and 4, or whatever it is. Okay. Now that you understand equilibriums, and you had some concentrations in here, could you figure out how much each one was? Yeah. Why? You could figure out the equilibrium concentrations. And if you knew the equilibrium concentrations, and you knew the initial concentrations, then you could figure out what these actual percentages are. So you don't have to just listen to me ramble off about 95 and 5 or 97 and 3 or whatever thing I felt like saying at that time. It was going to be relatively close. But now you'll know specifically this one is 96.7 or 85.2 or whatever it may be, because you guys now know how to deal with equilibriums. So ultimately in this chapter, we're going to get to this kind of thing. And if I were to do that, what am I going to need to use to solve something like that? Ice charts, absolutely. So that's where we're going to, just to give you a sense of why we did equilibriums first, and now why we're leading it into acids and bases, right? And this is going to change now. If I have something like equilibrium constant in an acid-base scenario, and I'm looking at the acid part, then I could call it Ka. And if I'm looking at the base, I can call it Kb. Equilibrium of the base, equilibrium of the acid, or whatever else. Okay, what's an acid, by the way, in general, that you guys know? How do you define an acid? Let me do that. It gives off hydrogen, so it's a proton donor is an acid, right? That's one definition.
It forms hydrogen ions or OH ions.
H3O plus hydronium ions in liquid, that's another definition. So your definition is specific to water, putting something in water. Your definition could expand a little beyond that by just the transfer of a proton, not necessarily one forming in water. Is there another one?
If it donates electrons.
So if something accepts an electron pair, that also could be called an acid. So there are different types of ways to define an acid. Maybe even more than that, right? Which is as many as we're going to go through. The first two are the more common ones. And if we did cover acid base, which I can't recall in 101, then those are going to be Arrhenius' equation, okay, which is what you were talking about. Yours was Lanza-Brouwer equation, Lanza-Brouwer. And the other one was what? Lewis, right? So there are three different definitions, and those are just the things that we're going to talk about now. So that it's a lighter section, as I said, which is nice since you guys aren't studying this part for your exam. So you have, I'm going to talk real briefly general properties, and here's Arrhenius acid bases, and then we'll talk a little bit from here acid-base strength, okay? Bronsted-Lowry acids bases here, Lewis acids bases here, another little discussion about acid-base strengths relative to this. Then we'll get into the molecular structure in order to see acid bases. When I say that, what comes to your mind when you think of acid bases? What types of acids have we seen when we did nomenclature in 101?
Hydrochloric acid.
We saw binary and oxy acids. And I did lay out when I talked about, I think, acetic acid, where the hydrogen is coming off on an oxygen, which is what makes it an oxoacid, and that's what makes it vulnerable to leaving that compound and forming that either hydronium ion in solution or donating the hydrogen in just in any system, whether it's water or not. So we'll see from the structure why and how some of these things come off. Okay, and that's what this section is. And then we'll get into a little bit of self-ionization of water and the pH scale, and even more than that. So there should be another. Then we're going to get into these things that I talked about here. So it's all leading up to this. And then we're going to look and we're going to see that things that things that you don't realize are acids could potentially play a role in making a solution acidic or basic, even slightly. And you'll figure out how to solve for that. And then when you talk about acids like sulfuric acid or phosphoric acid, so those have more than one hydrogen that can come off. We'll talk a little bit about that, right? In phosphoric acid, H3PO4, you potentially have three H's come off. And by the way, what is an H? H plus. Proton. So make sure, I know I emphasized this before, but in earlier classes, but I want to make sure you understand that H plus is just a proton. So when I say proton, and I mentioned to you proton transfer, that's what I was talking about, H plus, going back and forth, right? Everybody understands why an H plus is a proton, right?
Right.
It generally has one proton, no neutrons, and one electron, and if I strip that electron, it's just simply a proton.
Right.
Okay, let me make that clear for those of you that didn't have me in 101. Okay. And then we'll get into a lot of discussion about this, and you'll have to do sometimes multiple ice charts. And you remember when I said in equilibrium, where you really need to know what the chemical equation you're working with when you do the ice chart. It's going to become even more important here. Because as you get something like, say, you're looking at something basic and you have OH, and you have a compound, calcium hydroxide, that's Ca parenthesis OH in parenthesis 2, that's 2 hydroxides. In that context, you care more about the hydroxides than the calcium when you're looking at an acid-base reaction. So you have to count that as 2 moles of hydroxide, and having that lined up properly, and then going from what that creates to the next part of the equation is going to be a series of ice tables, and you have to understand what you're looking at in each one of those tables. So it's going to get a little more challenging in that concept. And of course, are we going to deal with, so KC, we also saw a KP, but when we're dealing with these, are we ever going to see anything like a KP? Are we going to care about pressure in these systems?
No.
So I wanted to put that in context of how we look. In all fairness, we really should have focused what on an equilibrium? KPs, not KCs, right? Because we were basically dealing with gases, not things that were in aqueous. But because this section is all about concentrations, then doing the KC made more sense, even though it's in the context of gases, just to put that in, some more practicality to how you would use it and why. Even though personally I didn't really need to use a lot of this for my type of research, but others may. Depends on the research you go into or what your interests are. Okay, real simple. General properties associated acids. Sour taste, change. So litmus paper, you guys are familiar with litmus paper. You can get a blue or a red litmus paper. And if you put it in a neutral or just water, then it doesn't change color. If I put a red in neutral system, it just stays red. It just gets wet, right? It looks wet, but it's still red. If I take the blue and I put it in, it's still blue, just wet. If I have an acid and I put the red litmus paper in, it just gets wet, it stays red. If I put a blue into that acid, it becomes red. And that's the indicator that this is an acidic solution. In doing that, there are also other types of litmus paper, and they're usually white strips that have a multitude of colors on them. And you put it in there, and then you match it up to the different levels of colors on the container, on the box. It's like a little plastic box like this. And you match it up, and then where it matches, you can estimate what the pH is a little bit more carefully, as opposed to just saying that it's acid or base with a red or blue. It'll say, if it's acid, it's going to be less than 7. It might be, say, 5.2 is what the pH is here. Having a digital thing where you wash the piece here and you put it in and whatever, give it digital, it'll tell you exactly. That's the best way to do it. But just for simplicity, I think we have little blue-red papers. If I put a blue in there, it will change that color blue to red if it's acid. So therefore, if it's base, which I'll do real quick next, then of course, if it's blue, it stays blue. If it's a red one, it changes to blue. Okay. They remain colorless in phenolphthalein. Brought up earlier, right? Phenolphthalein in an acid is colorless, in a base it's pink. Right? We saw that. And lastly, they react with bases to produce salt and water. That should be extremely obvious. I guess that these are very basic properties that you already know of acids. And now here are the ones of base, slightly different in terms of taste, bitter taste. I hope you're not tasting too many of them. Change color, litmus from red to blue, as we just described, turns phenolphthalein pink, and reacts with acids to produce salt and water. Same thing, very complex, right? Just like I said, it's lighter, right? This is nice because it's not too much to take in prior to your exam. Okay, some common acids in terms of what you might come across even in the household, things like HCl, sulfuric acid, nitric, acidic, citric, carbonic, hydrofluoronic and phosphoric acids. Here are some, and here are just some uses, metal cleaning, food preparation. You could find other things too. I don't know about you guys, my nose gets stuffy, always has since I was a kid, every once in a while, and I like to take those little nose drops and squirt it in. If you look at what, then it burns a hole through there basically, because it's HCl that I'm putting in there. But at least I know that. It's at a very small percentage. It's like 0.1% or 0.01% or whatever it is. But so there are other, if you look at your products and whatever else, you can see, what's in there. And you'll, sometimes if they're acids, you'll see things like this. I think we did something with acetic acid, I think. If not, that's in vinegar. Something like 5% of acetic acid is vinegar. That means literally, vinegar is acetic acid. It's just mixed with 95% water.
Right.
That's all. Fertilizer for nitric acid and some other things. I'll let you read this. It's not really useful to go through it, but just to give you a general idea of some of the common usage and where we come across some of these acids. Okay, so, and by the way, what I'm doing here is I'm walking you through things with acids, and I'll juxtapose sometimes, and I'll switch to bases. So keep your scope on what's an acid versus what's a base. Here I'm talking about acids. So what you've learned, and I think I just brought this up, is the binary acids and oxy acids, okay, if you recall.
Right.
Okay, so binary, something like this, HCl, right? Mm-hmm. And what makes something like a binary, first of all, when I just think of, this is a pretty simple system, right? Just HCl.
Right.
So what would indicate whether or not this Cl likes to hold on to this when I put it in water, or separate when I put it in water?
Electroaffinity?
Electron negativity?
Negativity.
Bond strength? Let me rephrase this. If I change that to Na and Cl, and I put this in water, what happens? It dissolves into its ions, right?
Right. Like this chart.
What about this?
It ionizes too.
What dictates the sodium chloride that it does that? Chloride is about 3.5, if I'll help you out a little bit here, electron negativity, right? So I have greater than a 1.7 or whatever it happens to be, 1.9 or whatever change in electron negativity, so it separates, right? How do I know that? I put it with apparatus and the light comes on if it's not plugged in. That's how I know I have ions. So in this case here, how do I know if I put this in water if it doesn't? Same thing, right? This becomes a plus, that becomes a minus.
Right.
Electron negativity, 2.1, 3.5, it's about a 1.3, 1.4 difference.
In that scale, yeah.
When I'm doing that, I have this system here, if you call this is a partial negative on that side, if I look at the H2O molecule, just assume that this is two-dimensional, obviously, but think of it as three-dimension. I have a negative down here and a couple positives up here. That means this side is more positive, that side is more negative, and I get the dipole moment going this way. Right? I did something like that multiple times in 101. So what's really happening here, I have two pairs of electrons somewhere around there. These things are out-competing this for this. It's a competition. I'm bringing up this type, and I'm describing it this way because this is going to become more relevant in a lot of other things we're going to do the rest of the semester. So having that perspective here will help you understand what's happening in a lot of these systems. This is just a competition between these and these or those or whatever. They're competing for this. Whichever one outcompetes wins. Okay, how does it outcompete? Well, it determines how strong of an interaction this can make versus how strong of an interaction that can make in terms of bonding. So the stronger this is, the harder it is for this to pull it off, the weaker the acid. Okay? Meaning that less of these come off. Because remember, a strong acid, you would have more of these. So I'm thinking about this in the context of the bonding patterns, the competition of what I'm interacting it with, and the strength of those bonding patterns relative to the ease of it releasing or not.
That's how we figured the strong and weak base acids.
Yes, that's where I'm going with this. So this is a strong acid because this thing outcompetes this for this and pulls it all off. Because it outcompetes it in water, aqueous, that makes this a strong acid because all of these leave that Cl, because the Cl is not very, it's a weak interaction between that and the Cl based on its change in electron negativity. Okay, why did I do this? Because it just somehow jumps here with structural formulas, and it doesn't talk about this first. This is the basic one. The second one are the oxyacids, and that's what you're looking at here. You're looking at a structure where you have hydrogens connected to oxygens, oxyacid. Those hydrogens are specified in the formula in the front of the polyatomic. Everybody see that? So these are the two that are here, and also the two that can come off that make this a strong acid. Now let's rephrase that though. H2SO4 is a strong acid for the first hydrogen. Do you think it gets easier or harder to get rid of the second one once you get rid of the harder?
Right.
Harder. So this is diprotic, meaning two, right? So the first one is actually comes off fairly easy because what's competing with it? Now you know why I showed you this model. Once again, the water. We're putting all these in aqueous, so they're all going in water.
Right.
Which is also interesting because all of the context this is in relationship to water. Can I put it in something else? Yes. Can I put a strong acid into a completely different thing and it could become a weak acid or a non-acid, right? Basically just a compound that doesn't separate. And still dissolve in it. I don't necessarily have to put it in like chloroform or something that is non-polar. I could put it in something polar, but am I going to have the same influence that the H2O has on this as what we're calling an acid? So keep that in mind. These are all in the context of putting it in water because it's competing with the lone pair on the water. So if I put it in something else, it may not be a strong acid anymore. It's only strong in relationship to being in water. And that doesn't say the S. It's not something you hear or read because you just making it simple, but it is something you should know. The context, which is probably why they don't explain this part in that interaction. That's huge. I think we do get into that a little bit later. But so here, I'm taking the water, I'm trying to compete this one off. Once this one comes off, that makes this what charge? Negative. Negative is going to be what? Is it going to shift the electron density this way or towards it? Away from it. Well, wait, right? Because it's more negative. The electrons in here are negative. So if they're favoring here, you got a greater negative charge here. It wants to shift it this way.
Right.
So then what does this one want to do? Shift it that way. What does that want to do? Shift it that way. Makes that one stronger. Okay, so you can see how some of these things work when you understand and weed out the structure a little bit. Does this make sense, what I'm saying? Okay, so sometimes I wonder if I go too far on this. But this is the whole practicality of it and the functionality of it. Otherwise, who cares? And then you just say, oh, well, HCl is strong because you told me it's strong. I want you guys to understand why it's strong. That's more important, because then I don't need to tell you. Nobody does. All you have to do is say, oh, what's going on here? What's the difference in electron negativity? Or where are these hydrogens on this particular thing? If they were connected to the sulfur, would they be in this complex or would they be over here? Does it matter what they're connected to as well? Absolutely. Right, so they could be a little bit stronger connected. If it's a carbon and the hydrogens are connected. Remember, I think I showed the structure of C2H3O2, the acetate, where you have the carboxylic group and the hydrogen coming up, but you have 3 hydrogens on 1 carbon at the end, right? Those carbons aren't acid carbons because it's hard to separate a hydrogen-carbon bond. So what they're connected to matters. That's why we call these oxoacids, because if they're connected to an oxygen, there's a good chance it's going to leave. And when they are connected to the oxygen, what are they usually connected to? A polyatomic. Keep that in mind also, right? Okay. So these are the hydrogens that come off to make it an acid. Here, HNO3, this is the one that comes off that makes it an acid. And in this structure, these structures, by the way, what else is nice about something like this is, and these are just things to think about. I don't recall if we get into these or not, but we should if we don't. This comes off more electron density, that moves over here, which then I have two bonds here. It's easy now to absorb some of that electron density this way because I have a lot of places to put it in that molecular structure, right? So we did in 101, didn't we?
Like the hybrid? No?
Didn't we do the hybrids and
Right.
we did the molecular hybrids and all that stuff, right?
Yeah.
So that's what this is. When you look at the three-dimensional structure here, you could see
In the hybrid.
how the, do you everybody remember that? How the orbitals work
Yeah.
in molecular orbital theory? A little bit? It's different than the atomic orbitals is what I'm saying. So that's why you can't look at this and say, well, you're looking here at an orbital of just the oxygen on its own versus the orbital of the oxygen within the compound. Right, the molecular orbital from the molecular orbital theory alters that a little bit. Can't remember, I know last semester we got cut off a little bit from the fires, and I can't recall if we got into this in class or if I had to just give you a paper that I sent out to everybody.
Oh yeah, the orbitals.
Maybe
was
that's
a
why.
paper,
So maybe
right?
I'll try to talk about this a little bit more as we go through, because again, I might have missed that section. Anyways, you're talking about the molecular orbital theory here, and you're talking about how the orbitals are able to delocalize the electron density so that it stabilizes the complex. When I say stabilize, that means makes it less energetic to hold it together.
Yeah.
Right? That's the whole point of it. Okay. And here's my acidic acid. So see here, these three H's here, these are connected very tightly, so these don't come off. This is the H being referenced here. That's why these three are within the compound, because they're not coming off as hydrogens in terms of making it more acidic. Only that one is, which happens to be right there. And then of course I lose that. Now in this complex, I could gain some, I could lose some of that electron density that I'm gaining here throughout this whole region here. And that reduces the energy needed to hold it all together, which is the point. By relieving some of that electron density all localized in one place, you delocalize it throughout the system. Okay, moving along maybe too slow. Okay. So here we go. These are the acidic hydrogens. Oh, good, David. So go ahead, David.
When you talk about like electron density, does that have anything to do with formal charges or?
Yeah, absolutely. We haven't got to, did we do formal charge in 101, right?
Yeah.
Yeah, absolutely. Yeah. So here, you know, what is the actual charge on this, right? And then you say, well, where are these at, the electron density favor of the electrons in the bond favoring this, and so we would assess this as the 2 minus, and that would make this, you know, whatever. Remember we did something like that? It absolutely plays a role. And that, the formal charges, then you look and you say, okay, well, this could be a couple different formal charges, right? And then you decide which one has the least energetic structure.
Yeah, more favorable.
Okay. What is this? Why is this different than the last slide? It's not. So that's this thing here. They're emphasizing here the hydrogen coming off of this structure. And all they're doing here is they're saying exactly what I just said, that this thing here comes off, and then this region through here can delocalize that extra electron charge. So instead of being localized here, it now comes here, which now it can distribute throughout this whole region. This whole thing is called a carboxylic group.
Mm-hmm.
It's one of the functional groups in organic chemistry. Did I cover organic chemistry in a little bit? I did that little section of
A
Chem
little bit,
in
yeah.
101. So you should know that this is a functional group from called a carboxylic acid. And in practice, or where you would see this, you would see this all the time in what? Amino acids, right? Amino acids have an N terminus and a C terminus,
Right. Mm-hmm.
right? This is one of the connectors right there. That's the carboxyl group. You also find it in a few other places, but that's the major one. Now I'm transitioning to make sure this is clear to bases. Those are some things related to acids. And if you notice everything on there, this is where it gets a little odd. That's why I started with what I did. I went off script from this, obviously, and I started telling you all the different types of how acids are, because the presumption in everything I just showed you is an acid is always something that gives up a proton. I'm going to give you that third definition where that's not always the case. Okay? And it's not the case sometimes, and you're going to see this with the bases, not because it doesn't create that, let's say, aqueous solution, it still could, even though it itself isn't giving up the hydrogen or taking the hydrogen or whatever else, it could be doing something to the water, because you notice the water also has hydrogens.
All right, right.
So even if it itself isn't giving up the hydrogen, if it pulls off a hydrogen in solution, it may be creating a hydroxide or something like this. See what I'm saying? So it doesn't always have to be giving it off or getting it. And that's what the other definitions will start to bring out. They may not be as obvious initially, and they're not as simple as just an H coming off or on or a proton, whatever. So here's some common bases. Sodium hydroxide, these are all strong generally when they have the OH connected to them. These things here are less obvious, but they'll, by default, they'll produce, like an OH in water. Once again, that's why it's specific to water that I'm talking about, because in something else it may not produce that, which matters. You get things like this ammonia here. Obviously, you're all familiar with ammonia detergent, things like that. You could read this. A little odd they put explosives here, but you can. I don't know why they want you to know that. Sodium bicarbonate, baking soda, that should be pretty, antacids. I don't know about you guys, I get that all the time. So I always gotta have, some kind of Tums or something around. So these are bases essentially, right? That's because my stomach's acidic, maybe I drink too much coffee, whatever it may be, and that neutralizes it some.
Question.
Go ahead.
Let's say a compound like in water that is not actually dissociating itself. Would the lattice energy of it cause also effects on the water?
The lattice energy is about the association of something, so it's already assumed to be associated before it got into the water.
Oh, okay.
And then if it's not doing anything to the water, then there's no more association.
Okay.
Right? Just in the very specific sense of how you're asking it.
Right.
Yeah. So these are some bases. There are also some organic bases called alkaloids. Bitter taste, often poisonous. They look like this, things like this. And the main thing about alkaloids, there are a variety of things associated with them, but the one constant always is that they're nitrogen. They have nitrogens in them. So that's the key to what an alkaloid is. Doesn't mean there aren't other things and other properties in each one, but to go over each one in some way is not really relevant here. But the main thing is they have nitrogens. And what I'm going to point out here is why that matters. And remember, these are bases now I'm talking about. It's transition from acids to bases.
Yeah. Make
Make sure we get that clear split, because that does become confusing later on if you haven't created that split yet. Let's just take a look at, say, ammonia. So the reason why I'm saying this is because we're talking about alkaloids, and I just said things that have nitrogens in them, and ammonia has a nitrogen in it. And on the outskirt, ammonia doesn't look like it would be a base, right?
Right.
Whereas, let's say,